To those of us who call ourselves geologists, the rock cycle is the most intriguing of all of nature's cyclic events. We can define the rock cycle as the set of processes that create and consequently destroy all of the Earth's crust over and over again. The rock cycle can really be characterized as a restless and dynamic process, one that involves billions of years of time and the recycling of large continental plates. It's important to note that the rock cycle is not really a simple circle traveling in one direction, but rather a web-like set of processes that go in a much more unpredictable manner. By making careful observations of the rocks that surround us, we can formulate conclusions about how they formed. In other words, we can figure out the past histories of rocks by looking at the clues that are locked within them. The three basic families of rocks, igneous, sedimentary, and metamorphic, all have those kinds of clues. For instance, this particular rock has clues locked in it that tell us that it was at one time molten. This rock was at one time part of a sand dune in a large desert. And this one was at one time buried deep below the Earth's surface and has characteristics indicating that it has been greatly affected by heat and pressure. And so join us as we investigate the rocks within these mountains in an attempt to unlock their secrets and learn the mysteries hidden within. At this site, all of the rocks have the same characteristic look. Let's make a few observations. First of all, there is a massive craggy appearance with jagged joints throughout. Secondly, there are no layers to be seen. And third, there is a multicolored speckled appearance to this rock type. Let's take a closer look. In order to do that, I'd like to break off a fresh piece, and I'll do that right here. Okay. There. At first glance, the rock has a very sparkly appearance. The hand lens will show us some interesting characteristics. I can easily see that there are crystals in it, crystals of quartz, feldspar, and mica, and these crystals have a definite interlocking pattern. The fact that they're interlocking is an important clue as to how this rock formed. If we could turn back the pages of geologic time, we'd see that this rock, a granite, began as a hot fluid called magma. Several kilometers underground, magma is stable as a liquid. But as it cools, slowly hardens into solid rock. This process is called crystallization. As the magma slowly cools, the atoms become fixed in an orderly pattern called crystals. These crystals grow in an interlocking manner, resulting in a jigsaw puzzle-like texture. This microscopic view of granite clearly shows the interlocking arrangement of minerals. Now, let's compare the granite with a different rock called basalt. The most obvious difference is that basalt has tiny, very fine-grained crystals, indicating that the atoms had little time to arrange themselves. Where do rocks like these crystallize? Where magma reaches the Earth's surface, it's called lava and is forced upwards through volcanoes and vents. The relatively cool temperatures at the Earth's surface quickly chill the lava into fine-grained volcanic rocks like this basalt. And yet, despite their different textures, granite and basalt share a common process within the rock cycle. They both crystallized from a hot, molten state. That's why we call them igneous, meaning born of fire. Regardless of the environment in which they've crystallized, all igneous rocks, when exposed at the Earth's surface, can begin the next step in the rock cycle. It's worth taking a second look at this granite because it helps illustrate a very important point. That is that granite like this is extremely hard, but like rocks exposed to the atmosphere everywhere on Earth, it will undergo a natural process called weathering. Weathering involves the breakdown of rocks from sharp, irregular, jagged outcrops like this to more rounded, subtle appearances, and eventually right down to fine particles in a pile. We are now at a location downhill and downstream from the igneous rocks we studied earlier. Here we can see what happens to the products of weathering as they're involved in the process of erosion. Let's take a closer look at this particular site. First of all, we can see that there is a variety of sizes of materials here, from sand-sized particles to obvious gravels, all the way to rocks the size of automobiles. Secondly, there are many different rock types at this particular spot. There are light-colored granites, like the one we studied earlier, and rocks even similar to the basalts that we looked at. And that's because this river, like all rivers, drains a wide portion of the mountains and delivers to us many different rock types. The third point is that the rocks that we studied at the previous locations were quite jagged. What has happened to them as they've traveled down the stream and had hundreds and thousands of collisions is that they've become more rounded, and there's also a tendency for them to become more spherical. All these clues tell us that these rocks formed somewhere else and were transported here by erosion. Erosion is an important link within the rock cycle as a means for removing and transporting the products of weathering from one location to another. The materials carried by streams and other agents of erosion are referred to as sediment. Keep in mind that sediment can be a mixture of many rock types. Another important step is the laying down or deposition of sediment. Here, rivers are eroding and depositing sand and gravel, but in other places, waves are washing sediment along beaches. Desert winds are piling sand grains into immense dunes. Or, in large bodies of water, mud or clay-sized rock particles are settling out and piling up on the bottom. Even fragments of organic matter can accumulate as sediment. Some deposits, such as lime mud, are derived by a purely chemical process. Lime, or calcium carbonate, can precipitate from seawater, forming thick deposits on the ocean floor. Regardless of their origin or composition, sediments stack up in horizontal layers, the oldest on the bottom and the youngest at the top. Given enough time, a stack of sediments like this can lead us to the next step in the rock cycle. This sequence of sediments is a good place to observe what really happens in nature. The layer down below, which is a very distinct sloping layer, is a lot like some of the sediment that we saw in the stream. The particles in here are sand size and larger, and yet the layer immediately above looks a lot more like mud, very finely layered. Let's take a closer look at each one. The layer down below me is different from the pebbly, sandy sediment in one major aspect, and I can show you that quite easily. It's extremely hard. It's obvious that it's no longer a sediment. Something has happened to this to produce a very hard type of rock called a sedimentary rock. This hasn't changed tremendously because you can dig into these layers, and those layers don't seem to be nearly as hard as the sandstone below. In fact, this rock breaks into very friable little flat pieces. The fact that it looks a lot like mud is a very strong clue to how it formed. The hardening of soft sediment into hard sedimentary rock begins when loose sediment fills a basin. As it does, the lowest layers become squeezed and compacted. In many cases, the circulation of water in the pores of sediment aids the process by precipitating or gluing the grains together with natural cement. This hardening process is called lithification and turns sand into sandstone, mud into shale, and lime into limestone. This specimen has clues that clearly illustrate the point. It contains pebbles that are now glued together or lithified to form a sedimentary rock called conglomerate. Let's now continue our investigation of the rock cycle by looking at the third and final family of rocks. The rocks in this gulch have some particularly interesting characteristics that we can observe. The first one that you can notice is that the rock has distinct and definite layers. These layers are an important clue as to how it formed. Another characteristic of this rock that's very important is the fact that it has crystals. You can't easily see it unless you break a fresh specimen of the rock, and I'll break this particular rock right here. Okay, in a smaller fragment you can see that the rock does have crystals. These crystals have a very important characteristic we learned about before. That is, they are interlocking. We call this type of rock metamorphic. Metamorphic, the word itself, means changed form. And the form is changed by heat and pressure, but it's important to note that no new elements have been added or subtracted. Because metamorphic rocks involve changes in form, we can in many cases deduce the types of rocks from which they are derived. In other words, for any given metamorphic rock, we can determine its predecessor or parent. For example, the specimen on the left is the igneous rock granite. Granite is the parent rock for this metamorphic gneiss. Look closer. You can see how these crystals have been squeezed into alternating bands of dark and light minerals. We call this layering foliation. A second example shows the changes in textures between the parent rock, a fine-grained limestone, and its daughter rock, marble. Its sparkly appearance indicates that mineral grains have been recrystallized by heat and pressure. And finally, the pebbles in this sedimentary conglomerate have been compressed and flattened by heat and pressure as if they were plastic. This rock can now be called metaconglomerate. And indeed, any rock that is made unstable by heat and pressure has the potential to be changed into a metamorphic rock. In fact, if temperatures are high enough, the rock goes beyond metamorphism and melts to become a magma. At this point, the stage is once again set for the crystallization of igneous rocks. What processes can accomplish these dramatic changes? To find out, let's look at the forces that actually power the rock cycle. It's part of a global process called plate tectonics. The theory of plate tectonics states that enormous slabs of the Earth's crust are constantly shifting, pushing, pulling, and grinding past each other. Along the edges of colliding plates, all rocks may be heated and squeezed into metamorphic rocks. In some places, these tectonic forces uplift mountains, which in turn are immediately attacked by the processes of weathering and erosion. Even deeper within the Earth's crust, rocks may remelt and then cool and crystallize into igneous rocks. Where plates separate, magma can reach the surface and then solidify into fine-grained igneous rocks. Although these crustal plates move slowly, the process of plate tectonics eventually recycles all of the rocks of the Earth's crust. We've learned how to apply our knowledge of how rocks form to create a new concept for us called the rock cycle. Remember, it's not one specific concept, it's a set of processes that take place all around the world at all times. Along the way, we've studied igneous rocks and seen how magma cools deep below the Earth's surface to form crystalline granites. We've seen how lava flows onto the surface to create fine-grained basalts. We've studied the process of sedimentary rocks and understand that weathering and erosion create sediments that are deposited in layers and then become solid rock. We've seen how metamorphic rocks are changed by heat and pressure deep beneath the Earth's surface. And we've learned how all of these can become another rock type as time goes on. We must remember that rocks, like other objects in our physical world, are capable of great change through time. How they're created, destroyed, and transformed is the dynamic story of the Earth's never-ending rock cycle.